Okay, hello. My name is Jillian Rastinashad. I'm a PhD student at Northwestern. And today we're going to be talking about short gamma ray bursts counterparts with the Gemini Observatory. So what are the systems that we're actually talking about? So thanks to the amazing event GW 170817, we know that two neutron stars emit gravitational waves that we can observe with our current gravitational wave observatories. When they merge, they emit these waves. They also emit jets along the poles. In addition to that, you have a short gamma ray burst with a duration approximately less than 2 seconds that's launched. And so we've been detecting these short gamma ray bursts for years, and they're another signature of these compact object mergers. So the jet eventually slams into the ambient medium, producing broadband synchrotron afterglow. And in addition, we have this kilonova counterpart. So these kilonovae are thermal transients powered by the radioactive decay of heavy R process elements synthesized in the neutron-rich ejecta. And so we know about all these counterparts because we observed them with GW 170817. So we observed them and we obtained these beautiful light curves. Seemingly every telescope in the world turned to look at this event. And we have a really rich data set that we can study and look for those heavy element signatures. So a key signature of a kilonova is this fast fading optical counterpart. Here you can see in the G band, whereas we have this longer lasting emission in the near infrared, which is a signature of the heavy lanthanide elements and their filled valence shells that increase the opacity of the ejecta. So why, a lot of you here don't study kilonovae. Why should you care about them? Well, they're the only known source of heavy R process elements in the universe. So R process elements, I think someone showed the periodic table the other day. You can see that the majority of the heavier elements were produced in these neutron star mergers. In addition, this R process enrichment affects the environment and the chemical evolutions of the galaxies in which they live. And finally, these kilonovae can actually offer clues to the maximum mass of a neutron star, being one of the few electromagnetic clues that we can get to the equation of state of these unique objects. So 170817 happened. We have this one really well-studied kilonova. And so now there's been a lot of theoretical work looking at what the diversity of these objects might be. So we think that not only binary neutron stars, but neutron star black holes can create kilonovae. We also think there's some diversity in what the remnant could be. So we could have a prompt collapse to a black hole, or a neutron star that exists that's rotationally supported for a few milliseconds before collapsing, or even a light enough neutron star that exists infinitely. So all of these different scenarios leave imprints on the kilonovae, and from theoretical simulations, we have different ideas of what those light curves might look like. So here are just some model light curves along with 170817, and you can see that all of them are fast fading, but they all span about 2 orders of magnitude and even fade at different rates. So all these light curves give us something that we want to study. We only have this one really well-studied kilonova, but we want to understand what the range of diversity is when we look at observations. So the Gemini Observatory is uniquely poised to observe these short GRB counterparts and can do a lot to help us when we want to look at this diversity. So the first way in which this helps is that gamma ray bursts can go off anywhere. Fermi and Swift find them all across the sky, as this map is showing. And so by having 2 sites in the north and the south, we're able to study these bursts no matter where, well, almost no matter where they go off. In addition, and this is something that Monica brought up too, having the rapid TRO capability and the diverse suite of instruments is really key to doing our science. So here on the right, I'm showing a plot of the afterglows that Gemini has discovered over the years. Approximately a third of the observed short GRB afterglows were found with Gemini. And indeed, you can see that these are really fast fading. The majority of them disappear within a day of the actual burst. On the left, I'm highlighting the Gemini spectra of 170817's kilonova. You can see that from the spectra, we were really able to match it to models, figure out how much of this R process ejecta was created, and the composition of it. And in addition to this, this event happened very quickly. We were able to get both spectra and imaging with GMOs and flamingos. So having these instruments available was really key to extracting the maximum amount of information from this event. And looking towards the future with instruments like Scorpio and our programs on JWST, these will continue to enhance each other. So the rapid TRO response is not something that James Webb has the capability to do, but Scorpio will do, and will study these beautiful broadband light curves. And then James Webb, our programs to study both gravitational wave and short gamma ray burst kilonovae at late times and obtain their spectra. In addition, short gamma ray bursts occur across a huge redshift range. And so not only are these things fast fading, but you want to be able to observe them and extract the maximum amount of information from them. So we need Gemini sensitivity and its ability to go deep in both the optical and near infrared. And so here I'm showing an image by our collaborators where they detected the optical afterglow and then the host galaxy spectrum of a short gamma ray burst at a redshift of 1.75. This is the second most far away short GRB that we've found. And NORAD did a wonderful press release about this for us. So you can learn a lot from these host galaxies. It's not what I study, but I want to highlight Anya Nugent has a poster that is going more into these, and we can learn a lot about the neutron star systems from their stellar population properties. So now we know everything Gemini can do, but here are some questions that lead into the research that we're studying. So how can we constrain the diversity of kilonovae with existing observations from Gemini and other large aperture telescopes? Is AT 2017 GFO a representative kilonova? And then how can we leverage Gemini's TRO capabilities to observe future counterparts to neutron star mergers? So I'm going to go over two different studies that we've done. One is a catalog and the other is a really exciting event. So, as I said earlier, SWIFT, the Neil Gehrels Swift Observatory, continues to localize short GRBs at a few arc-second precision. The GMOS imager and all of Gemini's imagers, are well equipped to follow up, unlike gravitational wave localizations. And so the detection of the short GRB is actually unique in that it allows us to explore kilonova diversity at a fixed viewing angle. So we think that the viewing angle can also affect what the emission looks like, but by studying these at a fixed viewing angle, we're observing the intrinsic diversity of the kilonova itself. So what we did is we built a short GRB kilonova catalog, and this is comprised of optical and near-infrared observations of 85 short GRBs over the last 15 years. So we get our data from unpublished observations, including a good amount from the Gemini telescopes. We get data from the gamma ray circular notices, which are real-time notices to the community of follow-up. And then we go through the literature. And so actually in our catalog are detections of kilonova candidates. So these are bursts where there has been photometric evidence for kilonovae following the gamma ray burst itself. And indeed, GRB 130603b is the first example of this. We have a very well-studied afterglow, and we see a nice near-infrared emission after it. In addition, what our paper contributes is a number of deep upper limits, which allow us to constrain the diversity of the kilonovae, even though we're not actually seeing it. And so together, this includes over 250 observations that span a wide range of time and the bands that we expect the kilonova to be observable in. And of course, Gemini played a huge role in this. A quarter of the host galaxy redshifts that we use in our sample are from the Gemini telescopes, and then a huge fraction of the most sensitive observations were obtained by Gemini using our rapid TRO proposals. So I'll go through some of our sample trends and the diversity that we were able to uncover. this plot, let me explain it. So on the x-axis, we are showing just time. All of the points on here are color-coded by the rest frame band. Our y-axis is the luminosity ratio, so the ratio of the observation to the ratio of the kilonova AT 2017 GFO, matched in rest frame time and band. And so things that fall along the 1-to-1 ratio here are basically tracing AT 2017 GFO. And so, highlighting some pieces of this. So the kilonova candidates, which are labeled in stars here, we see that the majority of them are detected at least in bluer bands, and they are more luminous than 17 GFO. We also see that there are a number of bursts which have deep upper limits that probe lower luminosities than 17 GFO. And overall, this shows significant diversity in the short GRB kilonova population compared to 17 GFO. So this is about a range of a factor of 2 in terms of luminosity. And again, this is not something that we're able to do currently with the GW observations that are out there. So just want to say that we do a couple other things with this huge catalog in our paper, but I don't have time to talk about them because I'll be talking about the really exciting recent discovery of the second closest kilonova to date that is actually following a long gamma ray burst 211211A. So I've been talking about short gamma ray bursts, and indeed this clear-cut picture of short gamma ray bursts and neutron star mergers is something that this event appears to revise. So this event has a duration of about 50 seconds, well outside that 2-second range of short GRBs that I discussed before. However, we obtained follow-up imaging with the Gemini telescope after hearing from colleagues that this event was happening very close to a galaxy at only 350 megaparsecs, which is one of the closest gamma ray bursts across both short and long categories. And so Gemini NIRI followed up this event at about 4 days, and we obtained this really nice K-band detection. And this was surprising because this does not, the optical afterglow was well faded at this point. And so we're seeing this near infrared excess that doesn't fit with what you expect the synchrotron afterglow to do. We continue to observe with Gemini. Unfortunately, there was bad weather. Luckily, our friend MMT was able to come online and help us observe. And then this really exciting event actually motivated mid-cycle HST follow-up. So we were able to get this nice HST image in the background. And what that confirmed for us is that this was by and large the most likely host galaxy. And this event, the luminosities that we were calculating from this transient were very close to what we expect for a kilonova. So next, showing the light curve of our event. So the points here actually afterglow subtracted. So we fit an afterglow model to the early data as well as the X-ray and radio data, and then we subtract that off. And then when we do that, these are our points here. The dashed line here is the kilonova that I've been talking about all along, but we just put it at the redshift of our event. And then the lines here are the model that we fit to it. And you can see just how similar, especially in K-band, this looks to 17 GFO. And you know, I was showing the 17 GFO light curves earlier. You can see that we're not, you know, we didn't get as many observations, but I can tell you as far as GRB kilonovae go, this is very well sampled. So so many amazing implications come out of this event. But as I said, you know, this looks like a kilonova, and we tried a bunch of other things to try and fit the data. Also, this has huge implications in the fact that this is a long gamma ray burst, implying that at least some fraction of long GRBs are created by neutron star mergers. And then also, really excitingly, some of our friends at LIGO calculated that this would have been detectable in 04. And so we're working with NORAD and NASA on a press release for this event, hopefully to be released soon. So I'll leave with my conclusions up here, but I do just want to say a big thank you to a large team of collaborators, and then our contact scientists, Kristen and Jen Andrews, who I know is not here, having a rapid TOO proposal, they are super useful and can always answer all the questions that I have. So thank you all.
Thank you, Julian. It's a beautiful talk. So let's see if there are questions online and in the room, please.
Okay, thank you. Great presentation, Julia. And I have a question that what makes GRB 21-111A has the long duration in gamma ray? Because it looks like originated from the binary transfer merger. So
Yeah, that's a great question. So we don't explore that in our paper. It's a great question. We do bring up two possibilities. So one is that this actually comes from a neutron star black hole merger. And so the tidal disruption of the neutron star produces that longer lived emission. The other possibility is that you have a magnetar run them. And so that magnetar, Brian Metzger has a 2008 paper that says maybe this is possible. Yeah, I would encourage you to look at those. There's also been a number of papers on the archive about this event now. So people have a lot of different theories about what could have caused it.
okay, so next question is quite tricky, but I just wonder, how can we discriminate those possibilities with the observational data? Is there any opinions or comments?
Yeah, so Ben Gompertz, he did a really detailed study of the high energy emission for this event. And so he set up this framework that can potentially look for these extended emission short GRBs. And so, you know, we don't, because most of these GRBs aren't happening as close as this one is. It's harder to get those time resolved X-ray spectra that he does. The other thing that I'll add is that you can detect supernovae out to farther redshifts than you can kilonovae. You can detect them with a telescope like Gemini out to like a redshift 0.5. And so I should have mentioned earlier, we don't see a supernovae for this. We did follow it up with the Nordic optical telescope. We have deep limits on that. And so you can constrain the massive star scenario by limiting the supernova.
Okay, great. Thank you.
Thank you for your question.
Anything online, Clara?
Nothing.
Nothing online so far. Anything else on the room? I'll ask a quick, more basic question to form. My understanding from years ago was that long gamma ray bursts gave us a very wide cosmological window. You could see all the way back to the epoch of reionization. What's our window, our redshift window for short gamma ray bursts and kilonova?
Yeah, thank you for that question. So long gamma ray bursts, because they come from massive stars, they trace cosmic star formation. So they peak at about cosmic high noon. And so again, want to point to Anya's poster because they make this huge compilation of short GRB host redshifts, and it peaks at about a redshift of 0.5. So there's these all depend right on the delay time distribution for the neutron stars to merge, and for those massive stars to evolve through and eventually produce the short gamma ray burst. So that peak is at about 0.5, which delayed from cosmic star formation can tell you a little bit about the delay time distribution.
Great, thank you. All right, let's thank Gillian again for a fantastic talk.